Hi everyone, I'm Xiaozhou. Today I'm going to talk about our final project, and our topic is model homophily and heterophily of graph data. My teammates are Yiting Dai and Yuan Haoshen. In our project, we designed a novel graph-neutral network for the representation of both homophily and heterophily of graph data. Our novel GNN model used a bikernel feature transformation and a selection gate mechanism, which can better model both the homophily and heterophily of graph data. Additionally, we've integrated this model into a user-friendly web application, which offers interactive graph data upload, analysis, and dynamic visualization using the G6 React library. Our web application is also a proof that our model has practical significance. I will first introduce the homophily and heterophily property of graphs. In general, homophily describes that the nodes tend to connect with similar others. This is observed in a wide range of real-world graphs, including the friendship networks, political networks, citation networks, and more. In opposites, heterophily describes that connected nodes tend to have different properties of labels, like dating networks. A lot of work has shown that common GNN models perform well on the homophily graphs, while have relatively poor performance on heterophily graphs. Homophily and heterophily properties should usually be quantitatively measured with an index homophily ratio that is formally defined as an average of the consisting of labels between each connected node pair. We did analysis on nodes, age, features, number of classes, and homophily ratio for the datasets. Homophily ratio represents the fraction of age that connected two nodes of the same label. If the ratio is close to 1, that means the dataset is homophily, and if the ratio is close to 0, that means the dataset is heterophily. We can judge from homophily ratios that Cora, Sear, and PubMed are homophily graphs, while Cornell, Texas, Wisconsin, and Actor are heterophily graphs. A lot of research works have proved that common GNN, such as GCN, has strong power to model the homophily ratio of the homophily property of graphs, while their ability to capture the heterophily property is often doubtful. This is partially caused by the design of the feature transformation with the same kernel. One kernel cannot model the similarity and dissimilarity between node features at a time. To solve this problem, we designed a novel GNN model based on a bikernel feature transformation and a selection gate. Two kernels capture homophily and heterophily information respectively, and the gate is introduced to select which kernel we should use for the given node pairs. Here's the overview of our method. Our model has two main modules, like the kernel selection gate learning and the bikernel feature transformation. The learning process of the kernel selection gate receives input graph information and output selection signal alpha to discriminate if the neighbor node labels are consistent. The bikernel feature transformation trains WS and WD, namely the ways to capture the similarity between nodes and ways to capture the dissimilarity between nodes. It uses the signal alpha from the former module to combine these two W in the process of the message passing, then doing mean aggregation, finally producing the node embedding. In the training phase, we have an additional cross-therapy loss to train the selection gate with separations. For the implementation of our model, we modify the message passing process in the Python geometric networks, adding a message negative function, which will be used with message passing function and aggregation process. In the training process, we will also compute a gate according to the similarity of the nodes with its neighbors, and we will add this part as a regularization to the loss. We compare our model with three types of state-of-the-art methods which perform well on the whole heterophily graphs, and 6 common graph neural network methods. They are like CPGNN, H2GCN, GMO-GCN, and DNN, GCN, GAT, GIN, and GIN2. And this table is our experiment results. So it shows the comparison of the mean classification accuracy of our model with other popular graph neural network models. It includes 3 types of reasons, state-of-the-art methods, and 6 graph neural network-based methods. In general, our model achieved the state-of-the-art performance on all of the 7 datasets. That means we can do well on both homophily and heterophily datasets. We perform experiments on 6 different speeds, in which the training set contains from 10% to 16% nodes on 4 datasets. These 2 tables show that our model has the best performance on most of the splits. On the homophily datasets, GCN2 achieved a similar performance to our methods. It is partially caused by the depth of GCN2 being much greater than ours. It is 16.4 layers, and our model only have 2 layers. On the heterophily datasets, our methods significantly outperform the baselines on different speeds. The results show that our model still have a decent gain when the portion of the training set is smaller, which means that we take good advantage of the labels, even though they are few. We also did other experiments like performance on the homophily and heterophily nodes of the graphs. I will not show here due to the time limits. You can find this part in our report. And this is the introduction of our system. So for the machine learning system, there are 4 parts: a data loader, modules, utils, and the training pipeline, which will use all 3. So this is our code. This is our report of the machine learning system. So it is contacted by the data loader, modules, utils, and node classification main file. And we will use NVIDIA 2080 Ti to train our model. We want people to easily use our model to do node classification tasks, like finding the category of a paper in a citation network. So we made a web application and applied our model. Users can upload their graph data on the website, and it will deliver classification results from backend applications. We used graph rendering engine G6 to render the uploaded graph data and classification results. On our web application, users can upload their dataset files in the format of CSV. Our application will render a graph with the uploaded data. Then the user can click the prediction button. This will trigger our backend to do the inference using our model. With the successful inference, the backend will send predictions results back to the frontend, and the graph with classification results will be shown. So it is our web application. Also, this graph engine provides users with interactively, such as you can drag in, zoom in, and panning, which helps users to explore the large graph. And this is all our demo. So thanks for watching.